right. So we're going to do some examples of these trig equations today. We'll do the quiz at the end here. Got 4 problems I'd like to talk about with solving trig equations. This will be some good review anyway as we go through. Because all we're really going to do in this particular section is add one extra little piece where we're going to use some identities to help us rewrite the equation in a form where we can actually solve it. So let's look at this first one. Look at this first one where we've got 2 sine squared theta plus cosine squared, plus cosine theta equals 1. Now we had a problem that kind of looked like this last time, but remember we had cosine squared and a cosine, and then we moved everything over and factored it. Okay? That is exactly the right idea, what you want to do here, except that I don't have everything in terms of the same trig function, right? So that's basically what we're going to do with these identities, is to try to make sure that we have the same trig function everywhere, so that we can do that factoring idea like we did before. Or if the arguments are different, so maybe if this were like now this isn't a good example, but like if this were a 2 theta rather than a theta, then I have an identity that I can replace sine of 2 theta with, okay? That's the idea. We want to try to make the functions match if we can, and also make the arguments match. So what can I do with sine squared theta in order to make the functions match? What can you replace sine squared theta with? Yeah, we replace that with 1 minus cosine squared theta. And now this looks a heck of a lot like the equations we were doing last time, doesn't it? Right? We tried to factor it if we can. Yeah. So distribute the 2 through here. So we get 2 minus 2 cosine squared theta plus cosine theta equals 1. Just so that I can get a positive coefficient on my cosine squared, I'm going to move everything to the right rather than move everything to the left. So when we do that, we should get 2 cosine squared theta plus minus cosine theta that is minus 1 because I'm subtracting the 2. Good, because it wasn't going to factor otherwise. Got nervous there for a second. So we get 2 cosine squared theta minus cosine theta minus 1. And now this, like I said, this now looks a lot like what we did last time, right? How does this factor?
And then cosine theta minus 1.
Good. And now set each piece equal to 0, right? When we do that, the first one should give us cosine theta equals negative 1/2. And the second one should give us that cosine theta equals 1. I know I skipped a step. So remember, when we solve these now, we want to find our solutions typically in 0 to 2 pi, but definitely in a period of the function, and then add multiples of 2 pi. So since I have cosine equals a negative number, we're looking in quadrants 2 and 3. If I use just a 1/2, what angle do you know has a cosine equal to a half? Pi over 3. So we need the pi over 3 angle in quadrant 2 and the pi over 3 angle in quadrant 3. What are those? Good idea. 2 pi over 3. 4 pi over 3. And then the last one, when is cosine equal to 1? 0. So that'll just be our multiples of pi then for that one. Or multiples of 2 pi for that one then. So again, notice there's not a lot different that we did in this problem, is there, than what we did in the previous section. All we did was just make sure that we wrote everything in terms of the same trig function to start. So, using that same principle, let's look at the second example. What do you want to do first?
Change the secant squared theta x in terms of tangent.
Good. So secant squared is
Tangent squared plus 1.
good. And I'll just rearrange. So secant squared is the same thing as tangent squared plus 1. So you'll have tangent squared x plus 1, and then plus that extra tangent x on the end. I just rewrote it so that our powers are descending. Now, the previous problem was nice because we were able to factor it. Unfortunately, this one doesn't factor. As a matter of fact, this may be even worse than that. That's okay. If something doesn't factor, but it's a quadratic, what can we always use? No matter what. You use your quadratic formula, right? So let's remember what your quadratic formula is off to the side here. What is quadratic formula?
X equals negative b plus minus square root b squared minus 4ac over 2a.
Over 2a, good. Sound familiar? Okay. All right, so instead of x, though, what's playing the role of the variable over here that we're trying to solve for? Notice up here, right, we factor with a cosine playing the role of the variable. Here, what's playing the role of the variable is tangent, right? So we use quadratic formula. We're not just saying x is equal to, we would be saying that tangent of x is equal to, right? What's the b coefficient in this case? It'd be 1, right? It's the coefficient on the tangent, so you'd have negative 1 plus or minus square root of b squared minus 4 times a times c. Well, your a and your c are also 1, right? Because the a is the coefficient on the squared, the c is the coefficient on the end. All over 2 times 1. What's wrong with this one?
There can be a negative on the
Yeah, the negative on the square root's a problem, isn't it? We're looking for real solutions to these problems. This is going to be negative 1 plus or minus square root of negative 3 all over 2, which causes a problem. So what would we say in this case? No solution. Good. So it would have any solution in this particular problem. So perhaps not the best example. That's okay. Didn't give me a chance to remind you about quadratic formula, though. Sometimes you have to use quadratic formula in these. If it did work, you would need to do the positive and the negative, do your inverse tangent on your calculator. Because we wouldn't have had one that we could do for an exact value for that one. But I probably wouldn't have had one. All right. Let's look at the next one. Maybe this one will be a little bit better. This one has cosecant t minus 4 sine t is equal to 0. Again, we have mismatched trig functions, so it would be nice if we could use an identity to write everything in terms of the same trig function. What identity might help here?
1 over sine.
Yeah, 1 over sine. Okay. So yeah, replace the cosecant with 1 over sine. Now we've got everything in terms of the same trig function. This should remind you of solving rational equations. Remember, the rational equations had, polynomial over polynomial involved rational functions. What was usually your first step when solving rational equations? What did you typically do first? Yeah, multiply by the denominator, right? Get rid of the fractions, correct? Now, anytime you do that, you have to be careful because the denominators here involve variables, right? So it's entirely possible when you do that, you might be multiplying by 0. It's entirely possible you could be multiplying by 0 when you do that, correct? So anytime that you have to do the clearing of your fractions to try to solve the equation, you need to check if you get those what we refer to as extraneous solutions. Do you get answers at the end that would have made your original equation undefined? Okay? So you have to make sure you check at the end, right? So for example, if we get any multiple of pi as an answer, we would throw it out in this case, because that would make the sign equal to 0. Okay? So it's just an extra step that you have to do whenever you do that. All right? So let's multiply both sides by sine. We get 1 minus 4 sine squared t equals 0. We've done ones like this before, right? Isolate your sine squared now. Subtract 1 and divide by -4 will isolate your sine squared, right? So you'll get sine squared equals 1/4. What do we do next? Square root it. You're good. When you take the square root of both sides, we get so you get 1/2. We also always get, when we take the square root, we always get plus or minus. So it'll be plus or minus 1/2. Notice in this case, it's positive or negative, so we're looking at all 4 quadrants. So in quadrant 1, sine is equal to 1/2 where? 5/6. And then in quadrant 2, we would use
5/6.
And in quadrant 3, we would use 7/6. In quadrant 4, we would use
11/6.
Good. Since it's plus or minus, we end up in all 4 quadrants there. And I know I wrote it as 2n pi as opposed to 2 pi n. I've been trying to use the 2 pi n because I believe that's what your book does. It puts the pi first and then the n. Of course, when I learned it way back, 7,000 years ago, you put the n before the pi instead of after. It wasn't quite 7,000 years ago, but 1988, 89 was a long time ago. Okay. Again, the last thing you should do, though, of course, is make sure that none of those made the original undefined, which it doesn't, right? The only thing that's going to make this undefined is if you got a multiple of 5. You have to be a little bit careful there, but not too bad. Any questions on that one? Well, let's do this last one here, and then I'll set you loose on your quiz. That sound like a plan? All right. What do you think we should do first? Say it again. Okay, we can certainly do that. Oops. Let me just subtract the 5, and then I promptly didn't do it.
One over 3 tangent for the 3 cotangent. We put it in tangent.
Okay, so do I move the 3 with it though?
No.
No, okay, because notice it's 3 out in front of the cotangent. So same idea. We want to make sure that we're writing everything in terms of the same trig function, right? So probably better to rewrite cotangent in terms of tangent. So you would have 3 over tangent. And then what's next? Okay, multiply both sides by tangent. So it clears the tangent in the first term, makes the second term 2 tangent squared theta, and makes the third term minus 5 tangent theta. And it's probably a little bit easier to see how this factors if I rearrange it.
Tangent theta minus 3. And tangent theta minus 1.
Good. 2 tangent theta minus 3 and tangent theta minus 1. Like I said, rewriting it probably helped a little bit to figure out how it factored. Again, if you don't see how it factors, you can always use quadratic formula. Always. However, more likely than not, on a quiz or an exam, I'm going to have you something that will give you some of the factors. I don't need you to try to go through the quadratic formula too. But you should remember that quadratic formula is a thing. Kind of an important thing. All right. So setting HP is equal to 0 and then isolating the tangents. The tangent theta equals 3/2 or tangent theta is equal to 1. Since we're dealing with tangent, we only need to worry about finding the angles from 0 to pi, right? Because the period of tangent is pi. Right? Let's look at the second one first because it's a little bit easier. When is tangent equal to 1? When are sine and cosine equal to each other? Pi over 4. So that one we could actually figure out the exact values for, right? However, we probably don't know when tangent is equal to 3/2. So this is when you would need your calculator. Do your inverse tangent of both sides. What do you get when you do inverse tangent of 3/2?
0.9828.
Okay. says or. It's an ugly looking or, but it said or. And again, we don't need to go hunting like we do with sine and cosine. Because again, for tangent, we only need to worry about all of the solutions in 0 to pi because that's the period for tangent, right? Once we find the solutions in 0 to pi, we can just add multiples of pi. It doesn't hurt to find all the solutions in 0 to pi. You just don't have to do that for tangent. Questions on that at all? All right. We'll do more of these on Friday.